Okay, let's take a look at the questions on page 225. Number 4, with a 300 Newton force, so F, 3 times 10 to the 2 is 300 newtons, a mover pushes a heavy box down a hallway. If the work done on the box by the movers is 1.9 times 10 to the third, so that is 1900 joules. You can leave it as 1.9 times 10 to the third if you want. Find the length of the hallway. Find delta D. And of course, we have to assume the angle is 0, that the mover is pushing the same way the box is moving. So W equals F delta D cos theta. And this is going to become 1. So delta D is equal to W over F. So 1,900 joules divided by 300 newtons. 19 divided by 3. And you should get 6.3 repeating meters. Number 4, done. Number 5. A large piano is moved 12 meters across a room. So delta D is 12 meters. Find the average horizontal force, so you're looking for F, to be exerted on the piano if the amount of work done by this force is 2.7 times 10 to the third. So W is equal to 2.7 times 10 to the third joules, which is 2,700 joules. And again, theta will be 0. So W is equal to F delta D cos theta. The cos theta will be 1. This time F is equal to W divided by delta D. So 2,700 joules divided by 12 meters. The amount of force you need is 225 newtons. I should probably check that, right? Because you're not here to tell me if I screwed up. Oh, it is 225. All right, number 6. A crane lifts a 467 kilogram, so 467 kilograms is my mass, beam vertically at a constant velocity. If the crane does, so the amount of work, 5.2 times 10 to the fourth joules of work, this time I'm going to leave it that way, it'll be too many zeros. Find the vertical distance. So if it's lifting at constant velocity, that means the force it's lifting with has to be equal to Fg, right? Some of the forces in the y direction will be 0, so F minus Fg. So mg, so 487 kilograms times 9.81 meters per second squared. 487, 9.81. So 477, so the force you're lifting with, 4777.47 newtons. Okay, and so now you do W equals F delta D cos theta, and the crane is lifting it up, and the beam is going up. So again, the angle is 0 degrees, so cos of 0 is 1. So this becomes delta D is equal to W over F. So 5.2 times 10 to the fourth joules over 4777.47 newtons. Delta D is going to equal 10.88 meters. Number 6. Number 7. A teacher carries his briefcase 20 meters down the hall. Delta D is 20 meters. And it's going this way. To the staff room. The teacher's hand exerts a force of 30 newtons upward. So F equals 30 newtons going this way. That means theta equals 90 degrees. And it wants to know how much work is done. W equals F delta D cos theta. If you want to fill it in, you can. W equals 30 newtons times 20 meters times the cos of 90, but you may have already realized the cos of 90 is 0, so the amount of work done is 0 joules. Part B says explain the results because the object isn't moving in the direction of the force, and therefore no work is done. Number 8, a 2 times 10 to the 2, so that would be 200 Newton force acts horizontally on a bowling ball over a displacement of 1.5 meters. Calculate the work done. W equals F delta D cos theta, assuming you're putting that force on the ball in the direction that it's moving in, then theta is 0 and cos theta is 1. So W equals 200 newtons times 1.5 meters. So W should equal 300 joules. Done. I should have been boxing these. Sorry about that. Let me go back and fix this up. And there's my force. And there we go. All right. Number 9 says, the Voyager space probe has left our solar system and is traveling through deep space, which can be considered to be void of all matter. Assuming the gravitational effects may be considered negligible when the Voyager is far from our solar system, how much work is done on the probe if it covers 1 times 10 to the 6 kilometers? So delta D is 1 times 10 to the 6 kilometers. And then just in case you were wondering, it's traveling at a speed v of 3 times 10 to the 4th meters per second. And it wants to know how much work is done, F delta D cos theta. But the key in this question, it says, assume that the gravitational effects may be considered negligible. And what that's saying is there is no force of gravity acting on it. This space probe is just an object in motion that is staying in motion. There is no force, therefore W is 0 joules. Explain the results obtained. No force, therefore no work can be done. Number 10 might be my favorite problem of all time. An energetic group of students attempts to move an old tree stump for use as firewood during a party. The students apply an average upward force of 650 newtons. So F equals 650 newtons. The 865 kilogram tree stump. Now, I'm not sure if you appreciate that 865 kilogram tree stump is 1,903 pounds. So this group of energetic students decide they need some firewood, so they go to get a tree stump that is 1,903 pounds. Like, what kind of fire are they trying to build? Like, anybody ever hear of, like, gathering branches? All right, so continuing. The 865 kilogram tree stump does not move after 15 minutes of pulling. Seriously, it took them 15 minutes to figure out they're not going to be able to move a 865 kilogram, 1,903 pound tree stump? Like, they might be energetic, but I'm not so sure they're that brilliant that it took them 15 minutes to figure out, I don't think we're going to be able to move this. We might want to go pick up those branches over there and use them instead. So the question is, how much work is done? Well, the key in this question, other than the fact that they perhaps are not that brilliant, is that the delta D is 0. They are not able to move it, and therefore the work done is 0. And your work on this page is also done. Okay? Explain the results obtained. They didn't move it. No work done. All right. Next page, new video.